Hi folks, Mr. Ackerman here. Thanks for watching. Topic of today's video is electric potential. And before we get started on this one, I have to warn you that while some of the terms are going to sound familiar, for example, electric potential energy might remind you of gravitational potential energy, there's a little bit of a curveball coming here, and that is when we start talking about something called electric potential without the word energy in it. There's nothing in the gravity examples that sort of compares to this, so keep your eyes and ears open. Make sure you're aware of when the question is asking you about electric potential energy and when it's asking about electric potential. They're not exactly the same, and if you don't pay attention to what's going on, you may make a mistake. Anyway, we'll try to avoid these mistakes by explaining the differences, so in a moment I'd like you to pause the video, have a look at some of the questions we're going to answer in this one, as well as where we are in the unit schedule and what the learning goals and success criteria are. Please do that now and then return. Okay, and you're back, and we're going to get started here. So here we go with our first slide. We're going to talk first about electric potential energy versus gravitational potential energy, and I'm going to refer to a graph. The graph comes from your textbook Physics 12 by Nelson, and a lot of things are going to sound really familiar. Let me explain. When we talk about gravitational potential energy, which we did a few videos back, we were talking about this formula. Eg equals negative g big M little m over the distance, which we sometimes use a letter R for. And if you want to see how to use this formula, of course, go back to the video on gravitational potential energy in general. We realized that there was a graph that went along with this equation, and if you recall, it looked something like this. We plotted Eg versus R, and you had a curve below the x-axis or the r-axis that looked like this. And we talked about how this was like a y equals negative 1 over x. We also talked about the negative sign here. We talked about how for reasons that have to do with calculus, you end up with a negative here. We also talked about how gravity is an attractive force. And as you're going to see, and as we have already seen, that negative sign has something to do with the attractiveness of gravity. So now what I'd like you to do is remember we've been talking about mathematical comparisons between gravity and electricity. Same thing is about to happen here. Just like Eg is negative gmm over r, Ee, which is called the electric potential energy, will be kq and a smaller q over r. Although here's where one of the differences pops up. While there's a negative sign in the gravity formula, there's no negative sign in the electric formula. And the reason for that is simple. If with this formula you include the sign, so include the sign, that's SIGN, plus or minus, for the charges that are involved, then look what happens. When you've got a positive and a negative, you end up with, of course, attraction, according to the law of electric charges. And when you multiply a positive and negative, you get a negative out here. So this equation behaves the way the gravity formula does in the case of attraction. That's why we don't need to include a negative here. It works itself out if you include the signs. And of course, if you have two positives, or if you have two negatives, then you're going to end up with repulsion. And of course, when you multiply two positives or two negatives up here, you will get a positive. So guess what? We're starting to realize that potential energy when you're dealing with attraction is negative in gravity, and it also comes out negative with electric charges. But there's something new here, almost like a repulsive gravity. Well, we don't have repulsive gravity, but we have repulsive electric charges. That will give us a positive potential energy. And so the graphs could be either sloping down from above or sloping up from below. So this image here, or this graph, which is taken from your textbook, does show you the two possibilities. All right, so take a moment to think about that, and then we will call that the first fact of the video, is just to know this formula here and that you have to include the sign when you sub in the charges. Okay, that's the first fact of the video, the formula for gravitational potential energy. Now you might be wondering, what exactly does what does electric potential energy mean? Well, it means pretty much the same thing it meant when we were talking about gravity. If you had two masses, big M and little m, like a planet and you, then this was telling you how much gravitational potential energy there was just because one mass was in the other's gravitational field. Well, similarly, we can have electric charges doing the same thing. Just like in gravity, you could say something like when a mass is held above the ground and released, it falls down. It loses gravitational energy and gains kinetic. We could say the same thing for electric charges. If they are opposite charges and they're attracting one another, then letting go of them when they're near one another will make them come toward one another. You will be converting E electric into E kinetic. Just like with gravity, you could have converted E gravitational into E kinetic. On the other hand, with gravity, you could take something and throw it in the air, throw it way up in the air, it will slow down and lose EK, it will gain EG. Well, same thing could happen here. You could have a moving electric charge being attracted back to some other electric charge, and as it tries to move away, it loses kinetic energy. We will have a gain in what's called electric potential energy. Of course, you could have this situation where like charges are already repelling one another, and if you release them, they will naturally fly apart. Again, you'll be converting EE into EK. It's almost as if you had a spring that was compressed and it was released and sprung outward, or in this case, you have a spring that's stretched, and as the elastic potential energy converts to EK, the spring snaps back. So let's do a simple calculation just to try to get a hang of this. Suppose you have, we've been talking about the hydrogen atom a little bit from some previous videos, so let's talk about that again. You've got a proton in the nucleus, and you've got an electron some distance away. In the classical model of the atom, in the Bohr-Rutherford model, this distance, I believe we saw, was approximately 5 times 10 to the negative 11 meters. And of course, the charge on the proton, which maybe we'll call big Q, is positive 1.6 times 10 to the negative 19 coulombs. And the charge on the electron, which maybe we'll just call little q this time, is negative 1.6 times 10 to the negative 19, same charge. So if I asked you for the electric potential energy in the hydrogen atom, you might answer this: K, big Q, little q, over R. And you would sub in 9 times 10 to the 9. Then you would put in your two charges, but you have to remember the signs this time, because we have to know if the energy is negative or is it positive, because that's going to tell us something that you'll see in a minute. So let's finish this off. We're going to divide by 5 times 10 to the negative 11, and let's do a calculation here. I'll just pause the video for a sec while I do that. You can do it too. Okay, folks, and the calculation for me comes out to negative 4.6, or that should be a 4, negative 4.6 to 2 sig figs, sorry about that, times 10 to the negative 18 joules. Now, what does this mean? Well, let's think for a moment. If the proton and electron were just sitting still, like let's say we just somehow held them in place this close to one another, forget the fact that the electron's supposed to be orbiting the proton in the hydrogen atom. Suppose these were any two charges and we just held them there or placed them there for whatever reason. Then the fact that they are opposite charges means they will attract. If I let go of them, they're going to move toward one another. They're going to start gaining kinetic energy. How much kinetic energy is available to be gained? Well, this calculation here is giving you an idea that there is roughly this much energy available to be gained. Now, what does the negative mean? You're going to have to wait a couple of lectures, a couple of videos to find out exactly what a negative energy would mean, but don't be too surprised because the same thing happened with gravity, where any two masses held close to one another will attract, and if you let go of them, they'll come toward one another. So we have seen this in the gravity situation. In a couple of videos, we're going to see this in the electricity situation. So stay tuned for that. All right, moving on. Next question that we'd like to answer is, what do we mean by electric potential? You notice I have dropped the word energy from here. Please note, electric potential is not the same as electric potential energy. What do we mean by it? Well, in the last example, you saw a proton with an electron near it, and we calculated the electric potential energy. However, there is a question along the same lines of this calculation that you could ask, and that question is as follows. Not how much potential energy is there, but how much potential energy, and so there is the idea of joules in this, but per coulomb of charge. And can you guess, will it be positive or negative coulomb? If you guessed positive, in fact +1 coulomb, then you're right. It's our good friend, the positive test charge. The positive 1 coulomb test charge. What we're imagining, or what we're answering, the question we're answering when we calculate electric potential is this. If that proton from the previous question is sitting here, never mind there being an electron here, I don't care that it's an electron. What I'm thinking of instead is at some point in space, right over here, which is, like before, 5 times 10 to the negative 11 meters away from the proton, how many joules of energy per +1 coulomb of charge? So what I try to do is imagine a +1 coulomb test charge sitting right here. And if you can do that, and then you calculate what's called the electric potential energy for that coulomb, you'll be getting something called electric potential. So since it's per +1 coulomb, we actually don't even need to include that number in the calculation. We're going to include, or we're going to calculate rather, Q, KQ, divided by R. We don't need the other Q here because it's the number 1. Another way to look at it is we'll be dividing it out of the calculation because per means divide. So this thing that you're about to calculate has a different symbol. It's the symbol capital V, and so we give it these heavy-duty little tick marks on top, whoops, just so that we remember it is not speed or velocity, it's capital V. And if you're wondering what in electricity was V, if you're thinking voltage, that is where we're heading here. So let's now see what the calculation comes out to. 9 times 10 to the positive 9. Again, include the sign of the charge. And finish off with the numbers, 1.6, 10 to the negative 19, divided by 5 by 10 to the negative 11. I'm going to pause the video here and do the calculation. You can do the same. Okay, folks, and what did you get? I got 28.8 as the answer here. And now it's not joules anymore. We've divided out the coulomb that came from any supposed second charge here. So this is joules per coulomb, or V, where V is volts. Okay, so a volt is a joule per coulomb. It's kind of like you make dollars per hour when you go to work. Well, here it's joules per coulomb of energy, or sorry, joules of energy per coulomb of charge, because you are at a certain point in the electric field. Okay, so pause the video and think about that for a moment if you have to see the relationship between electric potential and electric potential energy. They are different, although they are related. That is the second fact of the video then, to remember this formula, memorize this formula for electric potential. And just to go one step further, since we are dealing with a proton at this distance here, and in the previous question we did the proton with an electron at this distance, let me show you something interesting. Now that we know the potential right here has come out to a value of 28.8, joules per coulomb, or volts, we might ask ourselves, okay, so if you stick an electron there, how much potential energy does it have? Well, to answer that question, let's jump back to this slide here, where we said we've just realized that here there are 28.8 joules of energy available for each coulomb of charge there. And now we're going to reintroduce our electron. It has this many coulombs, and it's going to get this many joules per coulomb. So watch this calculation. If we do negative 1.6 times 10 to the negative 19 coulombs, which is kind of like saying you work a certain number of hours, and we give you credit of this much, which is kind of like saying we'll pay you this many dollars per hour, what do you get? Cross out those coulombs and multiply these out. What do you think you're going to get? You're going to get this number right over here. Try it on your calculator. You're going to see it's the same. In other words, this is trying to tell us something. The charge that you place at some location times the potential gives you the electric potential energy. I'll write that down on the next slide here. So this is the electric potential energy equals the charge you place there times the voltage at that location. Memorize that as well. That's very important. Now, to add one last thing to our arsenal of equations here, let's now talk about something called electric potential difference. I know in grade 11 you remember your teacher mentioning potential difference. They were always talking about potential difference, and so yes, things get a little more confusing. However, as math students, you know what to do when you see the word difference. That's the Greek letter delta, which means you do final minus initial. It's the potential difference, the difference in electric potential. So electric potential difference will be the delta in big V. It'll be V final minus V initial, which will be this number as a final minus this number as an initial, KQ over R final minus KQ over R initial, or since there's a common factor of KQ, you could call that 1 over R final minus 1 over R initial to make your algebra life as simple as possible. So, okay, I've just derived a formula for you that I don't know if you really understand what it means. It mathematically makes sense, but what's actually happening here? What are we suggesting when we say the word potential difference? Well, it goes something like this. Let's go back to this example of the proton and the electron in the hydrogen atom. Suppose you started off here where the potential is 28.8 volts. And now let's say for whatever reason you moved the proton somewhere else. Maybe the proton, the electron, for whatever reason picked up and moved further away from the proton. What would happen if you moved it further away? Well, its potential energy would certainly change. For example, in this formula for electric potential energy, when you increase the denominator, R, that's what we're doing here by moving away, when you increase that, you decrease the potential energy. Now, because it's going to be a negative number here, we go from, let's say, this negative number to a much less negative number. In other words, the electric potential energy increases. You've moved to a new location, which means the potential is also different there. In other words, there's been a change in the potential, or a potential difference. So this equation here is really for the movement of charge in an electric field. Anytime charges move through an electric field, if they move to different areas of different potential, then there will have been a potential difference. They will gain or lose electrical potential energy, as I just discussed here. How much will they gain or lose? Well, we're looking for the change in EE. In other words, we are looking for delta EE, the change in electric potential energy, will be the amount of charge times the change in potential that it moved through. So here is another formula to memorize. Change in electric potential energy, joules, equals charge, which is in coulombs, times a change in points with two different potentials, so joules per coulomb. Cross those out and you get joules. All right? So really, which formulas to memorize? Just to recap, this one, you can memorize this one if you want. Really, these two are very closely related. Remember what electric potential difference means and how we calculate it when we're dealing with point charges. I'll just connect those. Remember the simple formula for electric potential, and again, if you remember this, you'll easily be able to find these because these are just this final minus this initial. And of course, remember the formula for electric potential energy, but you will remember that because you'll think back to gravitational potential energy, and that will guide you and allow your memory work to be a lot simpler. Okay, so anyway, we're going to leave this now, and we're going to try a simple example. Let's go back to that hydrogen atom that we were talking about right back here. And just to remind you of what we did, I will just copy and paste this information onto the new slide. Okay. All right, so we're going to move the electron from where the potential is 28.8 to a place further away. Let's assume here that the final position is twice as far away. So instead of 5 times 10 to the negative 11, we're going to double that. Of course, doubling that gives us 10 times 10 to the negative 11, which is 1 times 10 to the negative 10. Sorry, what am I talking about? Yes, no, that is right. I apologize. We are going up in orders of magnitude here. Okay, so here is our final. So what were we calculating? Electric potential difference. So this is going to be delta V equals V final minus V initial, which of course is KQ over R final minus KQ over R initial. Now remember, we already found this. This number was calculated previously as 28.8 joules per coulomb, so I'm not going to do that again. What I want to do is get the new number, so let's continue down here. We have K, 9 times 10 to the 9, times the Q. The Q is think of it as the central charge, the thing you're moving away from, the proton, positive 1.6 by 10 to the negative 19. We're dividing by the final position, which is 1 times 10 to the negative 10, and we're going to subtract the number that we had here, which was 28.8 joules per coulomb calculated previously. I'm going to pause the video and do that calculation. You can do the same. Okay, and we're back here. Now, what did you guys get? Well, some of you were probably looking and saying, hey, you don't need a calculator. You don't need a calculator to do that because all we've done is taken the same number and double the denominator, right? We did this. What does doubling the denominator do? It makes the value half what it was before. So not surprisingly, I get 14.4 joules per coulomb at the new location minus the 28.8 joules per coulomb that I had at the original location. And what does that give me? It gives me negative 14.4, sorry, trying to write everything in here, negative 14.4 joules per coulomb, which is to say that the potential difference is negative. The potential has gone down, all right? Why has that happened? Think about it for a moment. We have had a situation where two objects were attracting one another, and we've moved one of them farther away from the other. And therefore, the electric potential has diminished. All right? Why do you think that would happen? Take a moment to pause the video and ponder a response, and then come back and we'll discuss. All right, and you're back, and let's discuss now. First of all, remember, in this calculation, we did not really move an electron from one position to another. We thought about what would happen if we moved an electron, but the electron charge is not part of this calculation. What we did was we just considered the electric potential at two different places and what would happen if you moved from one to the other. Remember also that electric potential deals with our good friend, the positive 1 Coulomb test charge. Right? If you were to take a positive charge and move it from here to here, let's think about what would happen. Here there would be a lot of repulsion. A proton and a positive charge very close together, lots of repulsion. Move this positive charge away and the repulsion gets less. In other words, there's a loss in potential energy. All right? That's why you're seeing a negative here. However, for an electron, what we can calculate from this, if I just sneak down here for a moment, we can do the following. We can calculate the change in electric potential energy, which is delta EE. Remember, going back a slide, that is, which slide was it on? It was right here. Delta EE is Q delta V. Let's see what happened not to the potential difference, but the energy difference. So here we go. It's going to be Q delta V, where now we're going to imagine an electron. So we're going to put in the negative 1.6 because we have to include sign when we're dealing with energy, times 10 to the negative 19, and we're going to put in this negative 14.4. Sorry if that looks like a 9, that's a 4. All right, and we're going to calculate these. I'm not going to pause the video for this, I'll just do it right now. I get a number of positive 2.3 times 10 to the negative 18 joules, which is to say, if I have an electron, the kind of thing that attracts a proton, and I move it away, which is kind of like taking a mass and moving it away from the center of Earth. Because remember, masses attract, so do opposite charges. If I move it away, what happens in the gravity example? You gain gravitational potential energy. You got a positive gain. Lifting something up gains it gravitational potential energy. Well, guess what? Here we also have a positive change in electrical potential energy. This example that I've drawn here is like lifting in gravity. So we would expect a positive delta EE. All right, so things are mathematically making sense, I promise you. If you're confused at what I just discussed, welcome to physics. If you're not confused, then you are either way more brilliant than I was when I was studying this at your age. Not to say that I was anywhere near brilliant, sorry, I'm not trying to brag here or anything. I didn't understand it as much as you're having trouble understanding it right now. What I'm trying to say is this stuff requires you to sit down and think really, really hard. You should not feel inadequate in any way if it doesn't make sense, what I've been saying. You should feel quite normal. I guarantee you that when you look around the room or when you're in university and you look around that big lecture hall, a lot of people are just as confused as you are. And really what separates the people who are going to be successful from those who are going to not be successful and who are going to stay confused is the people who are successful are going to sit down and struggle with this and work their way through it. That's really all there is to it. It's not that anyone is that much more brilliant or smarter than anyone else. It's quite often that they're just working harder. So if all of this was a little confusing, you may have to go back and watch it again. You may have to do some reading in a book. Maybe you don't like the way I explained it. You may have to do a lot of problems, but remember, your persistence will pay off. All right, enough of that little pep talk here. Let's go to an interesting application of this idea of electric potential difference. Remember we talked about oppositely charged parallel plates a while back. Well, here we've got them again. I'm just going to move this image to gain me a little bit of space here. This image is again from your textbook, Physics 12 by Nelson. It shows two oppositely charged parallel plates that are connected via a wire to what looks like a battery. from your grade 9 circuit diagrams, your grade 11 circuit diagrams. Remember, the long side is the positive, the short side is the negative. So what they're trying to tell you here is that plate A is positively charged, and therefore plate B is negatively charged. And they try to show you some sort of charge here, Q, and what are they saying here? Well, first of all, notice that the electric field is pointing to the right. The electric field is the direction of the net force, if you recall, on our good friend, the +1 Coulomb hypothetical test charge. So the lines here are showing to the right because that's a direction a positive charge would be forced. Naturally, the same way if you dropped a mass, it would fall to the ground. It would go in the direction of the gravitational field. Now, imagine that I'm in here, and remember that a battery, if you recall from grade 9 or 11, has written on it voltage, which is really potential difference. What they're telling you, when you go to the store and buy like a 9-volt battery, they're telling you that the potential difference between the positive and negative terminal is 9 joules of energy per coulomb. So, if we take a charge and move it from one plate to the other, we can say that there is a change in electric potential energy, which is equal to the charge that we moved times the potential difference, like 9 volts in the case of a battery you buy in the store. However, there's some other way that we can calculate the energy here. Remember another thing we talked about for parallel plates, which is that the electric field is uniform. Of course, it's not always uniform. It's only uniform in the case of parallel plates. I'll write parallel plates with 2 parallel lines here, and the word plates, just to remind you. Okay? The electric field is uniform for parallel plates. Now, if that's the case, that's like having a G value that is uniform. Think of near the surface of Earth, where we do 9.8 newtons per kilogram. Right? Same thing with electric field. We may have a certain constant value of newtons per coulomb. And in the gravity case, where we have a constant G value, that actually means that we have Fg equals mg. Well, in a similar way, we've got Fe equals QE. Remember that? I'm just going over this stuff because it's easy to forget. You're learning a lot of new things these days. So there's the force, which is constant, just like in the gravity example. So think about this. If I move a charge from one plate to the other, I do work. The symbol for work is W. It's equal to the force times the cosine of the angle, theta, between the force and the displacement. Now, as I just discussed, the force will be in the direction of the electric field, so we can put in QE. And you will either be moving, you're going to have to push the electric charge in the direction that it moves, so the angle here will be 0 degrees, which means we'll have a cosine value of 1. The delta D is the plate separation, and so let's put that in. Now in this diagram they use the letter R for the plate separation, and I wish they didn't because it makes you think of the R in here, and these are formulas where we're dealing with point charges. Here we are not dealing with one point charge, we're dealing with many, many, many point charges on each of the plates. So I'm going to continue to use the letter delta D. I hope you will forgive me. Let's just put it down there. Now the work done is equal to the change in electric potential energy, just like it was for gravity. So I've got this equals this. What's going to happen? I've got Q delta V in between parallel plates equals Q times the electric field times the separation of the plates. The charges cancel, and I get the following formula for the electric field between 2 parallel plates. So I'm going to write that as E, 2 parallel lines, equals the potential difference from one plate to the next divided by the plate separation. Here's a special formula for the electric field only between parallel plates, not the electric field due to a point charge. If you remember back when we talked about electric field due to a point charge, we had E equals KQ over R squared. These are not the same. Do not confuse these. I should have made this a fact of the video, but I guess we'll leave it as just something for you to remember. These are not the same. I see this mistake many, many times. A lot of people make this mistake. This is for a point charge. This is for parallel plates. And we're going to use this in our next lecture, or next video, where we're going to see a really cool experiment called the Millikan oil drop experiment. And we're going to be looking at an experiment that involves parallel plates, and therefore we're going to need to know the electric field between them. You take the voltage and divide by the distance, and you get the electric field. All right, one last slide to look at before we finish up. And what have we got here? A question from your textbook. This is question 8 in section 7.4 at the back. They give you 3 charges, a +4 microcoulomb, a -4 microcoulomb, and a +2 microcoulomb at the vertices of, or the corners of, an equilateral triangle with side lengths of 2 meters. So we can write that in. Maybe we'll put 2 meters with a tick mark, and a tick mark. All right, part A. Calculate the total electric potential energy, not electric potential, not electric potential difference, but electric potential energy. So this is going to be EE due to the group of charges. Now, how do we do this? Well, first, let's imagine if there was just 2 charges. So allow me to just delete this for a second. Imagine there were 2 charges. How would you calculate the electric potential energy? Easy. You would do something like KQ1, Q2 over the distance between them, end of story. But there aren't 2 charges, of course. There are 3. Let me ask you this question. What would you do if, instead of me deleting this charge here, I had deleted this? Now what would you do? You would use those 2 charges. Do you see where this is going? If you're going to answer this question, you have to calculate the electric potential energy due to the combination of charges. So here's how it works. Let's call this charge number 1, let's call this number 2, and let's call this number 3. We're going to calculate EE between 1 and 2, so I'll call it EE1, 2. K, Q, Q over R, where this is going to be number 1, this is going to be number 2, and this will be the distance B/W between 1 and 2. And looking at 1 and 2, I see these are going to be negative numbers, or a negative and a positive, so they're going to multiply to give a negative. However, now, if I take care of 1 and 2, what's next? I should do 1 and 3, right? So next up is E1, 3, because they contribute potential energy. So this time, this will be number 1, this will be number 3, and this will be R13, I sometimes like to call that. So we'll have the +4 microcoulomb, the +2 microcoulomb, 2 meters apart. And finally, the last combination is 2 and 3 down here. E23 equals K QQ over R. So you're going to do number 2, you're going to do number 3. This will be what I would call R23 if you like. And look at what nice things are about to happen. When you did 1 and 2, you had this and that. When you did 1 and 3, you had this and that, a +4 and a +2, separated by this distance. Now when you do the last one, you've got a -4 and a +2. So guess what? These two, which are separated by 2 meters, and those two are separated by 2 meters, are actually the same magnitude of, or the same amount of, same absolute value, I should say, of electric potential energy. They're going to cancel out. This one's going to be a positive, this one's going to be a negative, and they're going to be the same. So all you really have to do is this one, if you're looking ahead in this question. Okay, now on to part B. Determine the electric potential at the midpoint of each side. Now they're not talking about EE anymore. They're talking about capital V. Not a potential difference, just a potential at the midpoint of each side. So you got to do this 3 times, unfortunately. I'll show you what to do for the first one. Let's pick the midpoint of this side here, where we are 1 meter from that charge, 1 meter from this charge, and some distance from that charge. I think if you use a little bit of your knowledge of triangles here, you should be able to figure this out. It is an equilateral triangle, so I'll leave it for you to figure this one out. Anyhow, what do? We calculate the potential due to charge 1. Let's call it V1, which is K, Q1, over the distance of 1 from this point. Of course, there's also a potential contributed by this charge, number 2. So this is what we write. Notice how this is plus 4 microcoulombs at 1 meter. This one is minus 4 microcoulomb at 1 meter. So these two are going to be negatives of one another. They're gone when they add up. V3 is going to be K Q3 over R3. So this is the only one that's going to matter for this point. You're going to add these up. You might be wondering, what about the direction? And I'll be asking you, what direction? What are you talking about? Potential is a scalar. So just add those up. No need to worry about direction. We're not talking about force here or electric field. Anyway, they want you to do this for each side, so repeat on this side now. Do it for charge 1 at this distance, for charge 2 at this distance, charge 3 at that distance, and find a new potential at a new location. All right? And that's how that one is done. Usually confuses students, gives them a hard time. I hope this has made it easier for you. And that is the end of the video. Thanks for watching, and I'll see you guys in class. Take care.